Welcome to our beginning of our discussion of thermodynamics. It will actually span several chapters of our book, but we're going to start and focus on energy in this first part, and this will correspond to chapter 7 of our textbook. In section 1, we're going to look at energy and how we're going to be keeping track of energy and talking about energy, and hopefully it's mostly review from pre-AP. Okay. Now you know from physics, energy can be kinetic or potential. Examples of chemical potential energy is the gasoline you put into your car or the food that you eat that gives you energy when your body needs to use it. Have you ever really wondered where does this energy come from? If we say the gasoline I put into my car gives my car energy, what part of the gasoline is that that's giving my car the energy? So when we talk about that, we're actually, wondering how is it stored? If we call it stored energy, where is it coming from? Well, let's take a look at some examples. Okay. We're going to be looking at chemical energy associated with chemical bonds. So our stored energy is going to be stored in terms of stored in the bonds. Okay, so chemical energy is going to be dealing with chemical bonds. Now those bonds could be changed, they could be made or broken during a chemical reaction. And so people that study thermodynamics is studying how during a chemical reaction there's changes in energy. So let's look at some examples. We have this equation here, and that is the results of it. It's a thermodynamics equation because we know the amount of energy released. Here's a second equation we'll come back to in a moment, and there's another amount that's released. Now let's talk first off about just the first reaction. What is occurring in this reaction in terms of bonding? Notice I'm going from carbon atoms and hydrogen atoms and oxygen atoms to dimethyl ether, which is obviously a compound. When this occurs, we get this much energy released from it. So if energy has changed, what has changed in this reaction that would cause that energy change? I hope you said bonding. We have gone from nothing bonded to all of those atoms bonded together. So we have formed bonds. What is the result of forming bonds? We've got energy released. So let's turn this into, if I could spell, let's turn this into a rule. Forming bonds releases energy. All right, good one to note. Forming bonds releases energy. All right, now let's look at the second equation. In terms of bonding, what's happening? Will I be putting these together and making some bonds? Well, yes, I would be. But at the same time, the products are not just this dimethyl ether with this oxygen forming these two products. What has to happen for these products to form? Our dimethyl ether has to be broken apart, and then parts of that combine with oxygen to make carbon dioxide, and parts of that combine with oxygen to make water. So here we have both the making and forming of bonds. And notice how the energy associated with this equation is less. So why is it less? Well, previously we did nothing but make bonds, and that released energy. So if I have less energy, I had to do something other than just make bonds, and that is that some bonds were broken. So if I'm going to be breaking bonds, what I want to remember about that is that that must absorb energy. And that's why the amount of energy released in this reaction is less. Some of the energy that I would otherwise release is absorbed to break the bonds of the reactants in the first place. So now I have two very important rules. Forming bonds releases energy. Breaking bonds absorb energy. Very much like playing a game of Red Rover. You need energy. You need that momentum to break through the bond. In chemical terms, we need to put in energy to break bonds. And then to form a bond is super easy because it's going to release energy. It's actually a position of lower potential energy. but more about that later. Okay. Now, when we talk about releasing energy or absorbing energy, we can't just have it magically come from somewhere and magically go somewhere. So where does it come from, or where would it go to? That somewhere is called the surroundings. So we're going to be very much so looking at a system, which is the chemical reaction or reactions in question, and then everything around it is the surroundings. And the energy moving out when the system releases energy, or the energy moving in when the system absorbs energy, that is officially what we call heat. And heat symbol is Q, lowercase q, standing for quantity. So quantity of heat, an amount of heat. We can quantify it. We're going to put a number to it. All right. So please note before we continue that heat and temperature are not the same thing. Let me give an example. All right. Does 20 degrees Celsius water have more heat than 10 degrees Celsius water? So I have a container. Here's container 1. Here's container 2. Thermometer 1. Thermometer 2. This thermometer says 20 degrees. This thermometer says 10 degrees. Does this beaker of 20 degrees water have more heat energy in it than 10 degrees? Yes, it does. Does it have, according to the numbers, does this have twice as much heat energy as that? No, it will not. All right, so don't consider temperature to be a direct measurement. It is a comparative measurement. Please be very careful about that. Okay, so when objects gain or lose heat, we expect a change in temperature. But because temperature is not a direct measure of heat, I can't say that a 15-degree change meant that there's a 15 kilojoule change in heat or anything like that. There are other factors involved. The first one I want to talk about of the other factors is the amount of matter. And you should know this from experience. The amount of matter that's supposed to gain or lose heat will have an effect. So I have a bucket of water, and I have a swimming pool full of water. And they both start at 60 degrees on a sunny day. And they're both in direct sunlight all afternoon long. So they're both starting at the same temperature. They're both in the same situation, direct sunlight all afternoon long. Do I expect them to both have the same temperature at the end of the afternoon? And hopefully your experience tells you no. We expect the bucket of water to be warmer than the swimming pool. Why is that? The swimming pool has more matter, more water in it, and the bucket of water has less water. Okay, so typically the more matter in the system, the more heat it will gain or lose before changing temperature. The amount of matter, of course, is going to be measured in grams. We're going to measure the mass of the matter in grams. And there's the fact that all matter has this characteristic amount that is going to gain or lose heat. We call it specific heat. Okay. The typical abbreviation is CP. Okay, so specific heat at constant pressure, and that really doesn't mean a whole lot. So sometimes it's just C. They leave the P off. And in some cases, it's a lowercase c, some cases a capital P. Please don't let that confuse you. Okay. On the AP formula chart, it tells you very clearly in the formula what the C stands for, whether it has the P or not, and that sort of thing. Okay, so don't let that fool you, please. We can now, that we know all the factors, calculate what the temperature change would be. How much would the bucket of water change? How much would the swimming pool full of water change? It changes proportionally to the heat absorbed or lost, and inversely proportional to the mass and the specific heat. Now often what we will do, because it looks weird to see a formula that's a fraction like that, often what we'll do is we will write it as a single line, Q equals MC delta T. A lot of students remember this as Q equals MCAT, as if that was an A there. Okay, so Q equals MC delta T, where Q is heat, and we will use joules or kilojoules in this class. T is the temperature. We can measure that in Celsius. We could measure it in kelvins. That's a possibility. We could measure it in Fahrenheit. Don't know why in the world we'd want to, but we could. Your labels are very important. So in the numbers they give you, they would tell you what the label is. Just be sure that the temperature change okay, matches the label in your specific heat. As long as they match, you're okay. If they don't match, you need them to match, so convert something. And then M is mass in grams. Now, C, specific heat, is going to be measured in joules per gram per degree Celsius. What did I just say? Joules per gram per degree Celsius. It would look like this. We could measure in kilojoules. That's a possibility. Now, if I say it like this, joules per gram per degree Celsius, why would I write it like this? This is the way you are very likely to see it on the AP exam. I'm just saying. I've seen it this way, and it's very likely they'll do it this way again. Why not write it the way we say it? This takes up 2 lines of text. That takes up 1 line of text. They're much more likely to use the -1 exponents to tell you something is in the denominator of a fraction on the AP test. Because when you're printing hundreds of thousands of tests, every little line that you don't have to print is, of course, money saved. And they do really try to put that money back and lower the cost of the exam, if they can do that. So we now know heat, and we know how to calculate heat with mass, specific heat, and temperature change. We also know that when heat is gained or lost, it must flow from somewhere or flow to somewhere. So we could actually use that information to figure out how the heat in one area is going to affect another area. We could find the heat in part 1, whatever area that is, and see how it's going to affect the heat in part 2. And so we set the two Q's equal to each other. Now, why the negative? Well, heat lost is a negative sign. Heat gained is positive. So you have to negatize your negative to make them truly equal. It's a little math thing. Okay, so go blame your math teachers if you don't like what I just said. We're going to negatize the heat lost and set that equal to the heat gained. And because we negatize what will be a negative, we're going to end up with 2 positives, and they truly are equal. Now, why would this be a negative? Well, it's going to be a negative because for delta T, you're doing final minus initial. Over here, if it's cooling, that's a negative delta T. Over here, if it's warming up, that's a positive delta T. So mathematically, it really does work out needing that negative there. All right. So what is the negative showing? Well, the negative is really showing the movement of heat, whether it's coming in or going out. That's what it's showing us. We're not saying that there's such a thing as a void of heat or a inverse of heat. We're talking negative-wise about whether it's moving in or moving out. What would be the final temperature of the two things touching each other and trading heat? Whether it's hot and cold thing, or not so hot and not so cold thing, or cold and hot thing, if they're directly touching each other and they're allowed to let the heat move from one to the other, what should be true about the final temperature of both objects? Yes, if you wait long enough, both objects should end with the same amount of heat. That should be what happens there. Okay. Now, I also want to show you a variation of the formula we just talked about. What you notice is different. Oh, look at that. Our good friend the mole is now in here. Does that have an effect? Well, okay, instead of measuring in grams for the mass, you're going to measure in moles for the mole. And what else is that going to mean? Your label on your specific heat had better be in moles too, because again, those labels ought to match, whether it's grams and grams, or kilograms and kilograms, or moles, and the joules better match the joules. It is super important. I cannot stress this enough. Put the labels on every one of the pieces of this equation, because the moment you don't is the moment they won't match, and you're going to get an incorrect answer because you didn't bother to convert to make them all match. So what am I trying to say? Make them match. Joules and joules match, kilojoules match, moles and moles match, Celsius match. Be sure they all match. Be sure they would all cancel appropriately to get what you want. So we often call this the molar specific heat as opposed to just the specific heat, because now we're going to use moles for it. Okay, so that's where we're going to stop for part 1. I hope that makes sense. It actually should be pretty much just review from pre-AP. We've got quite a few practice problems and even some inquiry labs to do about it, so good luck.